Okay, you can see that the semester is drawing to an end. Okay, I don't take it personally. I blame the family exams. Okay, maybe I should take it personally. I don't know. So this week will be very simple. What we'll do today, we'll spend maybe an hour or something to still talk about various topics that are related to neural nets. These are, I think these are topics that are worth mentioning once, but it's probably, not topics that one spends a lot of time. It's probably very easy for you to just look at the notes, and it's things that you read, say, sure, okay. So we'll just look at them because they're important. You will hear them. You will, if you're in this field, you should know what they are, but they are not particularly difficult. And then we'll still talk about one topic which we'll start today and then finish on Thursday. And that has to do with graphical models. It's in principle a very large field, but I'll just tell you something about some very specific thing. We'll talk about base nets, but I'll tell you beforehand a little bit about the bigger picture and why these things are also important and also nice to know. Okay, so let's just do a small collection of topics that we still have for, mostly related to neural nets. Some are a little bit more general. So one is, we're talking about, so in the context of neural nets, we talked about the backpropagation, so how do we learn? And one thing I mentioned is that it's quite easy to add the effects of regularization, right? So what we did when we wrote down the backpropagation algorithm, we didn't have any regularization in there, but it's of course also one of the standard techniques to avoid overfitting. And so often you would still have some term, and so this term might something like whatever, some mu, whatever, maybe, let's just do it simple, let's just assume it's the wij squared. Okay, and so you go over all ij. And it might not just be like this, there might be weights for the various things. So you simply again do something that has to do with the L2 norm of the particular weights that you have. Now, for empirical reasons, it turns out that typically you don't put a penalty on bias terms. Okay, so that's just people have tried it out, and so typically that's people do not add bias terms. So I'm only writing here the wij. I'm not writing here, and okay, there should also be all the levels here. Okay, so if you go over I, L, and L, so over all the weights of all the edges, over all the levels here, but typically you don't put any penalty on the bias terms. Okay, empirically, you don't add them. Okay, you just put it on the weights. And so the question is, what does this change, right? Well, it changes hardly anything, right? Why, what would happen? So remember, when you do if you have your vector, let's say, at time, let's say t, let's assume that's the vector of all the parameters that you have, so all the w's, all the biases, and so on, right? Then, what is gradient descent, right? You take, what is the new vector? You take the old one, and then you go a little bit in the direction of the cost function, right? That's what typically you do. That's gradient descent, and you have a little bit you have some step function here, some step size, right? So now, what happens if you, how would you modify? If that's the gradient, the one, that actually has to do with without this thing here, right? Then how would this gradient be modified? How would the gradient change? So I want to add now. So let's assume I have only the weights right now. Forget about the bias terms altogether. Let's assume this theta is just all these terms here. And now this is the gradient with respect to the standard cost function that we had talked about last Thursday. And now I have this extra term here, right? This extra cost function. What's the gradient with respect to that? right? It's just, you know, if you take the derivative here, right, I get the square from this. This will cancel the half. So this will just give me the theta itself, right? Clear? So I have just this plus some theta at time t. Is that clear? Right? It's just that, you know, the square, take the derivative, I just get the term itself out, and the 2 will cancel the half, right? So this means, and this is of course at that time, you know, wherever I'm sitting right now at that time, right? So this means if I put this together, then I have theta t plus 1 is theta of t, and then I have here 1 minus lambda, right? So I take this and this, right? And then I have minus a little bit going the direction this. Right? So it looks essentially the same what we had beforehand. The only difference is that I have here, so think of lambda some small number, right? A small step size. I have this extra term here. And so this is sometimes called, and the only reason for writing down explicitly, this is sometimes called weight decay. You can see that the new weight is kind of the old weight, slightly, you know, multiplied by some number that's slightly less than 1, plus some new term here. Okay? So in itself, the math is completely uninteresting. You can do this in 2 seconds. It's just that if you hear the term weight decay, this is just, if you take a regularization term and then you add this to it, you just get the term itself in there. And the effect of it, of taking the regularization, is that you just think of the old term, you decay it slightly by some factor, right? And then you add the gradient to it. Make sense? The only reason to talk about it is that if you see it, you know that this is nothing else than just doing regularization. Okay? There's nothing more interesting or more different or whatever going on. You look puzzled. Yes? Can you just speak louder?
Yeah. So right now, so we are taking the old weight and we decay it. Why didn't we do that for, let's say, linear regression?
You know, it would come out to the same thing. It's just like, you know, this has nothing particular to do with the neural network one here. You know, if that how what it was, and this derivative was exactly this, the same thing would happen. Okay? So in that sense, it has nothing to do particular with neural nets. It's not really you do the same. We're just saying that if you take the standard thing and you do that, the effect of the thing is just weight decay. That's all I'm saying. That's irrespective. There's nothing particular about neural nets or anything. Okay? Makes it clear? We're just talking about it now. We just happen to talk about it now in that context. Okay? But it's more general. Good. Okay, so let's talk about some other things that you might come across. The next one is even more obvious, and you probably have already used this in, or hopefully maybe you've used this in your project, right? So data is expensive. Particular labeled data is typically expensive. And so one standard thing that you do, and that, again, is a general technique. It doesn't have to do with neural nets, is various techniques of data augmentation. And so what do I mean with this? Well, let's assume, for example, you have pictures, and maybe your task is handwriting recognition, right? And so you have pictures, and these pictures are various characters in here, and you want to train it, then we know that in general, the more data you have, the better job you can do, right? And that's perhaps even more important for something like neural nets that in principle have lots of parameters, right? And so the more data you have. So what are standard techniques to get more data? Well, you know, if you have this task, right, this is just a picture of a character here, then it's clear that if you take this picture, but you had taken the picture a little bit to the left, a little bit to the right, right? Or perhaps you had taken the picture with an angle, right? That these are all the same characters, right? And for us human beings, it doesn't matter, right? If I'm looking at this picture like this, or I'm stepping like maybe aside and looking at picture this is always a 5, right? But of course, for the computer, if I take that picture, or I take the picture and maybe move it to the left or to the right or up, or maybe turn it a little bit, these are all different inputs. And so often if you know that there should be some inherent invariance in the data, for example, invariance could be shift invariance, could be rotational invariance that you have, perhaps even some variance that you have with respect to scaling, perhaps an invariance that you have that you should still recognize it if you added, for example, a little bit some noise to it. Whatever it is that you think the task, this learning task should be invariant to, you can use due to this data and generate much more data from the given data. Make sense? Very easy, right? So you take this data, you can generate much more data from this data, train the network to it, and if you do that, and perhaps you take this, and perhaps you rotate it by all 360 degrees and give that, then you might learn a network, for example, that would be invariant to these kind of rotations, for example, right? And so maybe it's a slightly harder task. On the other hand, you have much more data and might be more stable, right? So it might not depend on the fact that you give it exactly like this. If you give it like this, it will still recognize it. Okay, so there are obvious things to do like this. There are some things that are maybe not so completely obvious to do. For example, you can run remember that we talked about PCA and we talked about compression of pictures. Okay, so you run a PCA and then you only keep the components that depend on the largest eigenvalues that you have. For example, you could take that as a picture, run a PCA, but only keep some, compress the picture, only keep a picture that only depends on the most dominant eigenvalues that you have in here, right? Now, for us, when you compress it and you do it right, the 5 will hardly change, right? That's the whole point of the PCA, that if you take enough components, it will be basically the same 5. But if you look at the pixels themselves, they will, they might move quite a lot, right? I mean, the whole function might change. So the computer, this might look like a very different input, and so this might be a new training data that you have by creating it, even though it's essentially the same. Okay, so there are some that are obvious. There's some that are slightly less obvious, like PCA or adding noise or some other things that you have, and it depends on the data and the function and the invariance that you might have.
So for example, if you take the number 5, you give it as a data set to your computer, you can also compute a PCA and double the size of your data, saying, well, it's basically the same elements, but I'm just giving you more data.
Yeah. Yes, so you create a much larger data set, right? From the data you have. And so then, of course, it's not a completely independent data set, right? So for example, if you just take the data and you add all kinds of noise to it, you might have more data, but the data itself is inherently worse. So it's not clear what is the trade-off, right? It might be maybe a little bit adding noise helps because you have a lot of new data and they're still good. But it could also be that it gets worse because, yes, you have a lot of more data, but each of the data is much worse, okay? So it's not completely clear, but it's worth trying out a few of these tricks. Make sense? Okay, again, very simple, very intuitive, and so depending on what the task is, just think of natural invariances, symmetries that the data has, and then you might take your data and adapt it according to these. Right? And now you can create much more data, and this might help you in training. Good. Okay. Now let's get to the first one that has to do actually with neural nets, and that's something that you will hear when training neural nets quite often. Here's another idea that people are using when training neural nets that will help it to prevent from overfitting. Okay, so it's a technique that is used to prevent overfitting. Just recall, neural nets typically have a lot of parameters, right? Even if you give it a very simple task like MNIST, you give it a reasonable sized network, could be thousands, millions, hundreds of thousands of parameters in there. And so, how can you prevent it from overfitting? You might give some penalty here on the weights, and another way to prevent it from overfitting is dropout. Now there are many versions of dropout, okay, so, but the basic idea is the following. So let's assume you have 2 layers here, and now you have you have all these weights here, right? You have this fully connected thing, whatever it looks like. Right, so this is from one layer to the next layer. So what you can do is now, you can either do dropout on nodes, or you can do dropout on edges. And what does this mean? It means the following. You have a current version of the network there. Okay, so there's a current version, architecture, weights, whatever it is, it's currently fixed. And now you want to train, you want to do the next stochastic gradient step. And so in the simplest version, what you can do is just pick some probability, maybe p. And maybe this p is whatever, 0.9, something. And so let's assume it's a version where we're doing dropout on nodes. Then what we do is the following. For each of these nodes, before we do the training, we independently flip a coin. And with 90% chance, we keep the node. And with 10% chance, if it comes up, for example, tails, okay, then we simply drop that node. Okay, so all we do is we flip a coin for each of them, 90%, so with probability P keep node, and with probability 1 minus P, you drop. Okay, so what drop means, you simply physically drop it and kill all the connections that you have. Okay? And so, so now what do you do then? You just consider the same net network you have. You just, but you have now a residual network, right, with all the things that are dropped. But every time you do it, you will drop different things because for every node, independently, you throw a coin or flip a coin and do this decision. So every time you do it, you will get a different residual network, right? And so now you have a residual network. And now for this residual network, you do one training step. Okay, so you just train as we did beforehand. Okay? And then you get back, okay? And of course, some of the nodes and some of the edges, you didn't change anything because you dropped them out. You get back the original one. Now you do a new dropout. You compute which ones now to eliminate, do another step, and so on. Okay, so there are two things. The one thing is, when you do this, you have to think a little bit about rescaling. So depending if you drop out nodes or you drop out edges, you have to be a little bit careful that you don't change the operating point. So let me just say what I mean with this. Let's assume you dropped out edges independently. Okay? And let's assume I have a node here. And this node has k inputs, right? Because this layer has k layers. So this node will have k inputs, and let's assume k is 1,000, right? Okay, so now with 90% chance, with 10% chance, I eliminate each of these edges here, right? So in expectation, I will only keep about 900 of the 1,000 edges alive. Make sense? Now, the important thing is that, of course, let's assume that each of them gives you, in general, a little bit some input. Now, it could happen that this input, for example, had a little bit some bias in there. It wasn't just like zero, wasn't just completely symmetric. Now, if I have 1,000 inputs or 900 inputs, will change, of course, the bias, right? Will change the operating term where you are. And that's crucial because remember, afterwards, after you add this up, you get this nonlinearity, and it's crucial whether you're operating here or whether you're operating here. Clear? So if you have that, and this might happen, what's important is that when you do the dropout, that you also make sure that you, for example, rescale. So, for example, what you could do is, if indeed you drop 10% of these things, then you should boost maybe, before you do the sum, each of the values by 10%, so that in expectation you get the right sum. Is that clear? Yes? Let's assume I drop half the edges, right? Then if there was a bias in these edges, then my expected value that I get in will be only half what it would be if I add all of them, right? Because I drop a random number of these edges. So in order to get back to the expected operating point where I am, I better boost this by a factor 2 so that at least in expectation I don't do anything terrible. Yes?
Can you just reduce the bias term?
No, it's one thing, but there's one is just the bias term itself. You're right, but I could maybe just do this, but I don't know. I don't know how much it comes from the bias term, and I don't know how much of the bias comes from the edges themselves, right? And so I cannot just boost the bias term by a factor 2, because perhaps the bias term is 0, and perhaps there's bias coming from the rest, okay? But it's not just this, it's not just the bias term. You also might worry, perhaps you don't just even want to match the bias, perhaps you want to figure out the variance of the things, okay? Perhaps you want to scale it such that the variance is the same. Clear? But you have to, when you do kind of things like dropout, you have to check, okay? And there are many versions, whether you drop the edges, you drop the nodes, you can have different probabilities for these, but you have to, clearly you have to be aware that when you do this, you're changing fundamentally the operating point, and you need to think a little bit about what you do to make up for this. Okay? So, there are many versions. You might drop edges, you might drop variables, and so the whole question is, why on earth would you do this? Why would you sabotage, your own neural network? Okay, it's already difficult enough to learn. And the reason is that when you do this, you can think of it in several ways. One is you can think about it that this gives you a more robust way of learning something. Since the network cannot rely on the fact to have exactly a certain structure, whatever it does, it better be somehow robust. Okay, so it's a robust way of learning. There's another more mathematical way, which we don't do here. If you think of if a neural network with a single hidden layer and a very particular activation function, then you can show that by training it in this way, it's equivalent of training many neural networks in parallel. And then, when you do the decision or when you do the final prediction, taking the expected or the average of all these networks. So what are these networks that you train? These are all the residual possible networks that you can get by dropping certain nodes. Is that clear?
Is that blending?
So I guess, I'm not sure it's called blending. Typically it's called, if you do the average, called bagging. Okay, so that's a standard technique called bagging. But what I'm talking about here is slightly different. Bagging typically means, perhaps it's also called blending, that I don't know, is typically when you train many models, maybe a neural net and maybe something else and so on. And then, as a final prediction, you take the average or you somehow take the weighted thing. Okay, so that's one thing. But here, this is a very specific way of doing it. We're not actually training these neural networks independently, right? We're training them all together, but it turns out that the effect for very specific things, so one hidden layer and a very specific activation function, you can show that this is equivalent of kind of independently training all these possible neural nets that you have, all the ones where you drop certain things. They have all different probabilities, because that you get a certain one from the original one depends on what you drop. There's a probability that you get this or this or this and this. And then at the end, the prediction is basically the expected value over all of these with these weights that you get. Okay? So you can think of it by training either as a robustness argument or that you really train many neural nets. And again, typically by doing bagging and by doing averaging, you get a more robust prediction. Okay? But this mathematical analogy is not true in general. If you have higher thing, it's kind of a guiding principle, but it's not exactly correct mathematically. Okay? It's one of these things that whereas in certain special cases you can show that, and then it's a guiding principle of why this might be something useful to do. Okay? Again, the basic idea is simple. When you implement it, of course you have to think about exactly how to do it. I'm sure there are packages that do this already for you, but if you hear dropout, you know that this is basically called dropout because you're dropping certain, during the training period, you're dropping random parts of the network, and the whole point of doing it that typically this gives you a more robust prediction. Okay? So far, that's what we need to know. Any questions about dropout? Yes?
Usually it's a good practice to disable dropouts when you predict, and then you just do it while learning the weights, and you don't use it in test time, but you're
so I didn't talk about the prediction. So again, how you actually predict, again, might depend. You can do the same thing for the prediction. You could also, in the prediction, predict based on many possible networks, or you could not, okay? Again, many possible versions, okay? Good. Okay, so dropout, I guess also fairly clear. Okay, now, okay, let me get now to one slightly bigger picture, and that's the last one that we need to do for neural nets. And that's a structural thing that you will see very often. And this is what's called convolutional nets. So again, this is things that you see quite often, and so things that you would see here also that, you know, weight sharing. So these are things that are quite important. Again, a very natural idea and a very simple idea, but a quite important idea. So what is this idea? Okay, so the standard thing that we have done is to think about a neural net in which for each of the hidden layer, I have the same number of nodes, namely k, and I have a fully connected network. Okay, so this is fully connected. And because it's fully connected, you have a lot of parameters, right? Because if this is k here, then we have, you know, just in the weights, we have a k squared parameters. That's times the number of layers that we have, and then we still have the weights. So if we have a lot of parameters and we don't have super much data, we might get trouble learning because, you know, if we have like 1 million times more parameters than data, perhaps it's quite difficult to figure out to get close to a reasonable operating point. So the question is, do we really need all these parameters, right? So the question is, could we maybe make do with a sparser set of connections here, right? So that not everything is connected to everything. And so there's, of course, many ways to do it, but one very natural thing comes from the idea of convolution. So what is this idea? Think of a discrete time signals. For those of you that have done communication systems or EE, that's something that you have learned, you know, from day one, and you know it's already bred into your, you know, imprinted into your brain. If you haven't seen it, you know, it's a fairly natural idea. And the point is like this. So let's assume I have a signal. So let me think of right now a one-dimensional signal. So X is our input. And let me just think about right now as a one-dimensional input. Okay, so, and let me just write down these components here. You know, in signal processing, typically you write it down more like x1, you use the square brackets. Typically we wrote x sub 1 and so on, just to follow the notation that's typically more used here. So it's x1, x2, and whatever. We have all these inputs, and let's just think of it as an infinite sequence right now. Okay, the boundaries are not super important, but I don't want to deal with the boundaries. So I have a one-dimensional signal. So what could this one-dimensional signal represent? For example, it could represent sound. Okay, so I have a sound wave. And so I'm thinking of a discrete version of the sound wave where I sample the sound wave at regular intervals. So these x's that I have are the value of the sound wave every whatever, fraction of a second. Now, the most common way of processing things like sound is what's called filtering. Okay, so this is, you know, this is the standard way of how you process something like this. So you put this sound wave into something which is called a filter. And what can a filter do? Well, you all know this from music. You can enhance, for example, low frequencies, let's say the bass in your system. You can enhance certain other frequency to hear voices better. You can denoise things. You know, you have all done, like, I don't, you know, in your whatever. In the past, you had this, you know, this mixing boards. If you're a DJ or something, now it's probably on some iPad, whatever. Okay, exactly, yeah. I can't do that, okay, but to demonstrate, right? So what do? You're changing which components, which frequencies of that signal are enhanced and which ones are suppressed. And so the way you do it is that you create from this a new signal. And so maybe this new signal is called y of n. And this new signal is what's called a convolution. And so the description is, I don't know what I use now for the filter, maybe h. So this is what the description is. Okay, so this is what's called a linear time invariant system. What you do is to compute the output at time n, you take the input and you do what's called a convolution with a particular filter or kernel. So this is the filter or kernel. So what could this look like? What this could look like is that this filter itself has some what's called impulse response. So these are values that you have. So for example, if you want to smooth the signal, all you do is take a filter that simply consists of 0 here, and then a constant over some part, and then 0. And all you do now is you go, if you compute the output here, you're averaging these 4 values that you have, and you get the new value. Okay, so just an averaging operation that you have. So this is what we call a low-pass filter. What you get after filtering, your signal would be smoother, right? If at the beginning the signal has a lot of things like this, if you smooth it, it would suppress high frequencies and enhance low frequencies. And now the signal would in general look smoother. Okay, and so there's a whole area of filter design. What should you pick this filter to be in order to achieve low-pass filtering, high-pass filtering, processing? And so the whole point is that it's very natural if you have natural signals like speech, but also pictures, that this processing should be local. Okay, meaning in order to see what my output should be at time t, this should only depend on the input at times that are close to the output that I have, okay? Just around, a few samples around, a few samples in the past, a few samples in the future. Make sense? Okay? So if we have that, then think of the following. So if we, for example, and so this whole thing is, I just wrote it down for you for a one-dimensional signal, but you can do the same thing for a two-dimensional signal. So this is, let's say, your picture. And now you want to do some smoothing, want to get rid of some edges, maybe you want to enhance the edge detection, then you can do the same kind of processing. And so you would have now a two-dimensional filter, which is something that's typically, down in some local area. This has certain coefficients in here, and what you do is now, when you want to compute the value here, you go over the old thing, put it over, take the average, take the sum over these points that are in there with the weights that are in this filter, and that's your output, okay? You just go over it, and you just compute locally what the new output is, okay? So that's a well-trusted, very useful operation to operate on natural data, like speech, video, photos, okay? So it's something that has been very useful, and you can do lots of things with that. So if that's a very useful strategy to do local computations around, then why wouldn't we try to do the same thing in neural nets, right? So if, for example, our input here is a photo, right? So let's assume our input here is a photo. And now think of the transformation afterwards, that's again a photo. Then maybe this no pixel here should not depend on all the pixels that I have here, right? But perhaps, if that's the point here, perhaps this output here of the transform should only depend on the input that are locally around this pixel, in the same way as we have the convolution. Okay, and so if you do that, then it means that now, to get to let's do the other way around. So now, if I have a particular, so let this pixel be now this, right? So now I don't go to all of them anymore, but I only go to a certain neighborhood. This is difficult to draw because I have a one-dimensional thing, and here is a two-dimensional thing. But I guess you can appreciate it. You would have in general here maybe 1 million such pixels. You have 1 million pixels here. Rather than going from here to all million pixels, let's only go to the pixels that correspond to a neighborhood around where this pixel is located. Okay? So what is the advantage? Beforehand, I had k-squared weights. Right? if I now take, for example, a neighborhood that is, let's say, whatever, maybe L times L, okay, maybe now I'm just looking at a neighborhood that is maybe of size, no, L is maybe not good. Let me just see what I use in the notes. Maybe I use capital K. If I'm now just going for something, now capital K is also not good because I use this here. Give me a symbol. Aleph. I don't know how to draw an aleph, okay? Give me some real symbol, come on. I guess it is the most real symbol you can come up with, but forget about that, huh? Alpha 4 is for real things. I need an integer. Okay, omega, I'm not gonna argue. Okay, is it capital omega or small omega? Capital omega, okay? So maybe I have a capital omega times capital omega grid, and this might be a 10 by 10 system, okay? So it means that now for every node here, I only have omega squared, or maybe 2 times omega squared, connections to the past. So now instead of having k squared connections, or weights, I have only k times omega squared weights, right? And so if k is maybe 1,000,000, but omega is maybe 10, that makes a huge difference. Clear? And the reason that we think it makes sense is because, you know, there's 100 years of signal processing, or how many years there were, and people built pretty good systems of transforming images and speech and so on by using exactly that kind of structure, okay? And so it makes a lot of sense of putting that structure into a net. And it's called a neural net because we're using, it's called a convolutional net because we're using exactly these kind of idea from the convolution to build our structure here. But it gets even much better, okay? There's only the beginning. Now, let's assume I take a picture, okay? So I'm here, okay? I'm taking a beautiful picture of you, okay? And now I do click, and that's the picture, okay? And now I process it. So now it turns out that somewhere I process a pixel here, right? And now, you know, this pixel here will then have certain weights attached to it. So let's assume it's this pixel here. And it will have certain weights attached to it, and I will learn these weights. Now, let's assume I'd taken the picture just 1 microsecond later, okay? And moved the camera a little bit and did click, okay? Now, the same pixel that I have now, the same one in the index, will actually look at a different portion of the photo, right? So if I learn certain weights here, then, you know, these weights should be kind of shift invariant, or it shouldn't really depend on whether I take the picture here or here or here, right? Because where this pixel lies in the thing is not really, you know, depends on how good I am as a photographer and not like what the neural network does. Okay? So this means that you might even be able to compress it to something much smaller. Rather than taking this and for each of them having different weights, why not have a single weight matrix of omega times omega and using the same matrix around every point? Clear? Okay, so every point now in the output doesn't get its own weights, but it gets the same weight matrix everywhere. So now we've reduced something that was k squared, where k maybe was 1,000,000, to something that's omega squared, where omega is maybe 10. Okay? So it's a huge reduction in the number of parameters that I have to learn. And so from that, I might hope to learn with many fewer parameters. Okay, so now there are 2 questions. Number 1 is, we learned this beautiful algorithm, the backpropagation, how to do, you know, the derivative with respect to the weights. So the question is, can we still use that? And the second question is, perhaps we have gone slightly overboard from going from 1,000,000 squared to 10 squared, okay? And so for the second question, what people do is the following. First of all, you can make the neighborhood slightly larger or smaller, but it might not pay off to make it too large. The other thing is that what very often people do is that based on one thing here that's maybe a size, you know, this 1,000,000 times 1,000,000 the pixel, you go to the next step here, but you take the same weight matrix, so you have only 100 parameters in here. But perhaps that's too little information, so how can I get a little bit back more? Well, I can do the same thing not just once, but twice. Okay, so going from one plane to the next plane, that's called one channel. Okay, you go from one thing to the next with one filter that maybe only has 10 squared parameters. Okay, so you have, so pictorially, you have one plane here. You go perhaps to the second plane, and there are very few parameters going from here to here, just 10 squared. But perhaps that's too little information. So perhaps let me learn another filter that might also be useful. So perhaps I don't just learn here one channel, but perhaps I learn here 10 channels. Okay, so each channel comes by the same mechanism from here to here via a convolution that has only 10 parameters. But I have different parameters going from here to here, then from here to here, then from here to here, from here to here, and from here to here. Okay? And so that way I can basically, how many parameters I have, I can just vary at will, right? I can make this bigger or smaller. I can take as many channels as I want, okay? And so there's something else also that comes in that should be fairly clear. If I do this thing here, and now let's assume you have, that's my weight matrix, right? And so now I go, okay, so everything is fine, but what do I do if I'm suddenly up here, right? There's no data out there, right? In order to compute something, I take a box, I center this box around this point, and I take averages around every point. But what do I do at the corner? At the corner, on the left and on top, I have no data, okay? So something has to be done. There are many things you can do. You can imagine that the data outside is 0, okay? And think of that as the data. You can perhaps not compute data where you can't compute it. So meaning perhaps you go from one plane to a plane that's slightly smaller, and you only compute it for points that are a little bit, you make it smaller, so that for all the points where you can do it, you still have the data. So it means the picture wouldn't look like this. The picture now would look that you go from one plane to many planes, but each of the plane is slightly smaller. Okay? And so if you go on, what you would get is like a pyramid. You would go from one plane to several planes, but slightly smaller, to even more channels, but even smaller, etc. Okay? So this might look like a pyramid construction. Many possible ways of doing this, and people have tried out billions of them. And so you can see that now you can do potentially with many fewer parameters than before, but it is meaningful because people beforehand have figured out that these are good ways to process images and sound. Now, we still have one question, and that's an important question, and that is, can we still use the backpropagation algorithm that we had beforehand, right? Because remember, if we go backwards, so now what happens, if I'm here, and I'm, let's say, here, right? Before, and when I did backpropagation, I looked at the derivative with respect to this edge here, I got something. And if I computed back the derivative with respect to this, I got some other values, and this is what the backpropagation gave me. But now what we are saying is that these two values must actually be the same, right? Because we're using what's called weight sharing. This filter here and this filter here are identical. So there's this edge, which is maybe the same as this edge, and this edge is maybe the same as this edge. And so the question is, what do we do? Can we still use something like backpropagation, but now we have the restriction that these edges are not, they cannot take on any value, okay? Certain edges have to take on the same weight, because by definition, we assume they have the same weight. Make sense? Okay? Psst. Okay. Okay? So you have now 15 minutes. Think about it, okay? And then we'll talk about it, okay?